Hello my people, it's now time for everybody's favorite, some trig-based related rates problems. Yes, alrighty. So let's get started. First one we have here, let me zoom in just a smidge. A man, 2 meters tall, walks horizontally at a constant rate of 1 meter per second toward the base of a tower that is 23 meters tall. Okay, and they've sort of given us a little bit of a cheat right here. If he's 2 meters tall, then only 23 meters of that tower is above him. So if we're looking at the right triangle, we have a 23 meter side to the right triangle instead of a 25 meter. So they've helped us out a little bit by drawing us the picture. Yay, them. When a man is 10 meters from the tower, when the man is 10 meters from the tower, at what rate is the angle of elevation? Angle of elevation is right here, theta. Changing if that angle is measured from horizontal line joining the top of the man's head to the top of the tower. Okay, and that's basically where they get the 23 meters from the 25, right? Because they're not talking about the angle of elevation from his feet. They're talking about basically how high does he have to cock his head to see the top of the tower. Now, let's go ahead and state our given. Okay. Well, the thing is that there's one constant for this right triangle, and it is the height from the top of his head to the top of the tower. The other two sides of the right triangle, here we'll call x, and this side are changing, okay, because he is walking toward the tower. Now, we don't need the hypotenuse. This is not a Pythagorean theorem sort of thing. And our given, of course, is our DXDT, how fast he is approaching the tower. Now, if this distance is x, then his rate at 1 meter per second is negative because he is making that distance smaller. Now, the question, okay, is at what rate is the angle of elevation changing? Right? At what rate is the angle of elevation changing? That is our question. That is, what is d theta, dt. d theta dt is going to be what we're looking for. And the conditional, and so they kind of mixed it up here a little bit. When the man is 10 meters from the tower, when x is equal to 10 meters. Alrighty. Now, if I'm going to be dealing with theta, I need to choose if I'm going to be dealing with trig, I need to choose a trig function which will model these circumstances, okay? I'm dealing with x. I'm given x here. I'm given dx dt here. I don't really care about this length. According to theta, I'm only interested in the opposite and the adjacent, which means that I need tangent theta is equal to opposite over adjacent. Okay? Or, you know, if you want to, it can become tangent theta is equal to 23x to the negative 1. Okay, well, let's see what happens when I differentiate with respect to t, and let's see whether I have everything that I need. This becomes secant squared theta times d theta dt, and that is equal to negative 23 times x to the negative 2 times dx dt. Okay, well, I have d theta dt, or I'm looking for d theta dt, so I should assume that I don't have it. I have x and I have dx dt. The only thing I don't have is theta, but I have a particular scenario of that triangle. And at that particular scenario, at the time when x is equal to 10, theta will have a very particular value. I'm not looking, however, for the value of theta. I'm looking for the value of secant theta. And if I'm looking for secant theta, now 23 squared, okay, You should know that. If you don't know that, how do we get at it? Well, remember that there's really two ways to do that. You know that 25 squared is 625, right? And therefore you know that 24 squared is going to be 625 minus 25 minus 24. Okay? Now that is 576. 23 squared is going to be 576 minus 24 minus 23. So that is basically, that's 67 right there. I mean, that's 47, 47. So what we have here basically is 625 minus 100 less a few, right? Less 1, 2, 3, 4. So basically what you have here is you have 529. Now the other way that you could do it, of course, is just 20 plus 3, 20 plus 3, and then you FOIL it, and it winds up being 400 plus 60 plus 60 plus 9, but either way you're going to get 529. So those are two ways to sort of do it in your head if you forget that 23 squared is 529. Now, that means that plus this side is going to be 629. So this is the square root of 629. Now, what that means is that hypotenuse over adjacent is root 629 over 10, but its squared is 629 over 100. I'm looking for d theta dt. This is negative 23. This is 1 over x squared, so 100 meters squared. And dx dt is negative 1 meter squared. Okay, so d theta dt ought to be, now those two cancel each other out, right? And so I'm going to get 23 over 100 times 100 over 629, and that's going to be 23 over 629. And basically, since, remember that radians are kind of not really units, but kind of units, right? What we have here is this is going to wind up, oh, by the way, since this is meters, this sort of carries on the whole way. That and that cancel with that, and so you're just left with something per seconds. Well, you know that it's going to be radians. So radians per second, and that right there is your answer. Okay. Now, thankfully, it didn't have a radical in it because this radical right there got squared with the secant squared. But this should basically, and that's a nasty fraction, but, you know, it's not like you're having, you know, radicals of, you know, 4-digit numbers involved in the, with pi's and e's and powers and, you know, other roots and stuff like that. It's just 23 over 629. So, and we can plug that into our calculator and we can get a decimal approximation. And of course, you would give me the sentence to answer the question. But let's go ahead and move on. The area of a triangle. Now, it says an isosceles triangle has equal sides 4 centimeters long, and the included angle is theta. If theta increases at the rate of 2 degrees per minute, at what rate is the area of the triangle changing when theta is equal to 30 degrees? Okay, so we have an isosceles triangle. Sorry, I'm just trying to make sure that I don't totally blow the proportions like I did on some of the cones in the last one. Okay, this is 4 centimeters. This is 4 centimeters. This is theta. Okay, now basically what's happening is you just, basically the base is dependent upon how open theta is. And of course, as theta opens more and more and more and more, not only are these two 4 centimeter sides going to swing out, that is going to make either the base rise towards that vertex or the vertex drop towards the base, whichever, right? But basically, you need to figure out how to deal with the area of this triangle. Well, let's go ahead and figure out the givens first. Now, the given is d theta dt. D theta dt is positive 2 degrees per minute. Well, when we deal with trig, we don't deal with degrees. We deal with radians, okay? And so what you're going to need to do is you're going to need to convert that to radians. And so basically that winds up being, now remember that when you try to get rid of degrees, you need to divide by the degrees, 180, and multiply by pi. And so this is basically pi over 90 radians per minute. Alrighty. Now, what question we're asking is, at what rate is the area changing? So you need dA dt is equal to question mark. Now the condition, okay, conditional is at what rate is the area of the triangle changing when theta is equal to 30 degrees. And I guess we really didn't have to change it into radians as long as you're being consistent and as long as you flip your calculator over to degrees and remember to switch it back. But I'd rather convert to radians, always work in radians, and just keep my calculator in radians, okay? Now, at what rate is the area changing when theta is equal to 30 degrees? So theta is equal to pi over 6. The question is, how am I going to calculate this area? Now remember, the normal area formula for a triangle is 1/2 base times height. But the height and the base are both changing, and basically we're given these two sides and the included angle. So I'm going to go for the 1/2 AB sine C formula, at which point this actually becomes, for our purposes here, 4 times 4, which is 16. Those are your A and your B, and its included angle is theta. So this winds up being 8 sine theta. Okay, for something that seems so difficult, that's actually a relatively easy equation to deal with. We have dA dt is equal to 8 cosine theta times d theta dt. And I'm looking for dA dt. dA dt is already isolated. Let's just go ahead and plug in 8 times cosine of pi over 6 times pi over 90 radians per minute. This winds up giving you centimeters, right? Because that's the original. It's the original up here. So this right here, remember, is 8. The units that goes along with that is centimeters squared. Now remember, because radians is sort of like a pseudo unit, it sort of evaporates in the midst of all of this. We need to remember that cosine of pi over 6 is √3 over 2. And so what we have here is we have 8 times √3 times pi, all of that over 2 times 90, and that winds up being centimeters squared per minute. And all I really need to do from here is just reduce, right? Now, 8 is 2 times 2 times 2. 90 has at least one 2 in it, doesn't have 2, so we can get rid of 4 and leave that as 2. And so we wind up with 2 pi √3, and the only reason I put the pi there is so there's no confusion as to whether it's underneath the radical, over 45, and that's centimeters squared per minute. Okay? And all we had to do was had to remember this area formula right here. We knew that this area formula wasn't going to do us any good. We needed to use this one. And in terms of this particular thing, like I said, this is your A, this is your B, that's your C, because A and B will be the sides on either side of angle C, which is its included angle. And of course, since those are constant right there, you wind up getting A and B as constant, and you really have an equation of only 2 variables. No substitution necessary, no nothing. We just go ahead and differentiate, plug stuff in, and just grind it out. Okay. Now, and actually, and actually it did become necessary to change it into radians, because degrees are sort of an artificial unit that wouldn't evaporate like radians do, right? Radians evaporates and is a pseudo unit because basically radians is sort of communicates a fraction of a full revolution. Like what fraction of 2 pi, a full revolution, is this angle? And as such, because it's sort of built into the logic of the circle itself as a unit, it sort of pops in and out of existence. Okay, and degrees would not be like that. So it was necessary on second thought, because I did have to plug d theta dt into here, even if I didn't wind up having theta, because theta was evaluated. It was cosigned basically. Alrighty. Let's look at this one. Now this is a very standard problem when it comes to related rates and trig-based related rates problems. A lighthouse is located on a small island 2 miles off a straight shore. Okay, so let's do the little lighthouse, and it's bright and everything like that. Like I said, not an artist. Okay, that is 2 miles from a straight shoreline. Okay, actually the shoreline's not an imaginary, so it's not dotted. But this right here, okay, is 2 miles. The beacon of the lighthouse revolves at a constant rate of 6 degrees per second. Okay, so basically our given is d theta dt, and it is 6 degrees per second. But of course, we don't want it in degrees, we want it in radians. So we are going to basically multiply that by pi over 180. Now, pi over 180, 6 over 180 is going to reduce to 1 over 3, so it's over 30, so pi over 30 radians per second. Now, my question is how fast is the beam of light moving along the shore? So here, basically, as it spins around, right, it comes around, and the beam of light will hit the shoreline and will sweep across, right? So where it hits, and I'm going to do it from the base of the lighthouse, just because, to make the triangle, because it actually is, if this were like bird's eye view, you wouldn't actually see the lighthouse, you just see a circle because you'd be looking down on it. You get what I mean. Let's call this right here, this lateral distance, x. Basically, x refers to how far up the shoreline the beam of light is hitting from the point, basically directly onshore from the lighthouse. Now, how fast is the beam of light moving along the shore at a point 3 miles from a point? So basically the question is, what is DXDT when x is equal to 3 miles? Now, is DXDT positive or negative? Well, in this case, it doesn't really matter because, first of all, you don't know you don't know whether it's 3 miles this way or 3 miles this way. You also don't know which way it's spiraling around. So it doesn't really matter, okay? It doesn't really matter. So we're just going to deal with positive values in this. But again, since I don't really care about the hypotenuse, it looks like I'm going to be dealing with, and of course this is theta right here. Theta is basically the sweeping out of the beam of light. Since I am not dealing with the hypotenuse, I'm going to have opposite over adjacent. So tangent of theta is equal to opposite over adjacent. That means that I can go ahead and do 2 miles times tangent theta is equal to x. And that's nice because last time the x was in the denominator. We wound up getting you know, a negative exponent and stuff like that when we differentiated. Okay, well, let's go ahead and differentiate and see where we are and whether we have everything that we need. So this becomes, and I'm going to just remember that that miles is there. So this becomes secant squared theta d theta dt is equal to dx dt. Now, at the particular moment when x is equal to 3, I have a very particular triangle, right? So I'm going to go ahead and draw the particular triangle over here because just like last time, I need the hypotenuse in order to get my secant squared. At that particular moment in time, it's 2 miles to the shore, 3 miles down the shore. That's going to be squared to 4. That's going to be squared to 9. And this is going to be root 13, okay, which is, you know, between 3 and 4. So we have 2, and the secant squared is going to be, now remember, theta's over here, not down here. So the secant squared is hypotenuse over adjacent. So that's root 13 over 2. But the quantity is going to be squared. And so it's going to be 13 over 4. Now remember, this is miles. And d theta dt is pi over 30 radians per second. And this is dx dt. Well, dx dt is isolated. That's kind of nice. This 2 cancels with 2 down here. And I'm left with 13 pi over 60. 13 pi over 60. Again, the radians as a unit, or as a sort of pseudo unit, is going to evaporate, and you're going to get miles per second, and that is your dx dt. And you can get a decimal approximation, and then you would just write me a nice little sentence explaining what that value means and how it is an answer to the question. Okay, it would be something like the beam of light is moving at a rate of 13 pi over 60, or the decimal approximation if you so choose, miles per second along the shoreline at that moment, right? So we're going to go ahead and call it quits to this video, and we'll do a couple more videos. I have a pile here of sort of representative questions on trig. Some of them a little more commonplace, some of them a little more quirky, but I think the sum total of them will give us a good appreciation for how trigonometry-based related rates questions sort of operate and how they're likely to be asked. Okay. As always, if you have any questions, please do shoot me an email. Bye.